Let me try one more time. I think I just, there we go. Okay. All right, so there we go. You can see the words if that helps. I know for many of us it does to see the words that are being spoken. We're trying to think of all the different types of learners out there. So when I was preparing this talk, I looked at my title and I thought, who's going to come to this talk? Maybe I could have given a better title. In any case, I'm glad you all are here. Otherwise, I probably would have titled it something like Invisible Mars, all the science on Mars you never hear about. Because most of what you know about Mars is the stuff you see. But because of that, because we're very visually oriented, I will kind of start us off in that arena. So I have a couple goals for this talk. One is what's science without having fun and making connections. So I hope you all have fun today. Also, I hope we're here to learn about Mars. If you are here to learn about other things, you can stay, but that's not my goal. Also, I know a lot of you are educators and I'm doing STEM education, and so I also have added some links so that if there are things that you like, you can use them in the future. Okay. All right, so if you don't know about the NASA Mars Exploration Program, I want to tell you just a brief I just want to make you aware of it. It's the part of NASA that thinks about Mars and funds all these rovers. And what you probably didn't know is besides rovers, NASA also funds satellites to orbit Mars. And not only NASA, but India and the Arab Emirates are also funding. They're also funding satellites to go to Mars. So Mars seems to be the place to go these days in the space world. These are the current programs that the Mars Exploration Program is funding. And you can jot down this URL if you would like to visit that website. So one thing I thought, Stephanie, maybe, if I'm on a slide for long enough and you think anyone might want to go and explore the website, maybe you could type it in the chat. Not, this one isn't one of those, but there are some coming up. Maybe that would be helpful to people. Okay. Is that good?
I'll do that.
Okay, great, thanks. All right, so just to give you context, I'm very much a context type of person. Some of you may be as well. Here are all the different locations on Mars where the different rovers have landed. And you probably have heard recently in the news that Perseverance is the latest rover to have successfully landed on Mars. And it's this giant rover that I'll talk briefly about, because before we talk about the atmosphere, and the air of Mars, let's talk about the ground. So here's a cartoon, essentially, a very nice one, that NASA put together that kind of shows the rover before it actually left. So this isn't a real image, although it looks pretty good. I think the Mars Perseverance is amazingly cool. They had to do some JPL, and NASA had to do some amazing feat. The engineers put together this amazing feat to get this rover on Mars successfully. And that happened earlier in the year. It landed in this location. And so this is one of these websites that I would love for you all to have this link, because it's an interactive website and you can go there and basically zoom out of this location and zoom in. So you can get kind of a context for where Perseverance is. It's in this crater. There are craters nearby, quote nearby. I mean, it's a giant planet. So it's not like you would walk to this crater here if you were over here. But I mean, you could over time if you could breathe, which you can't. So we'll get into all that. Okay, so did I give you enough time to type that in? I can also, okay.
It's in the chat.
Awesome, thank you. So I love this picture. If you zoom in to this location where they landed Perseverance, the reason they landed it in that area is because there's this amazing delta, this ancient river delta. And I just think the image here is so spectacular. This shows clear evidence of running water at one time. These are the kind of deltas that we would see here on Earth when we look at deltas from space. And so that's just one of I don't know, a million, thousands of pieces of evidence that really indicate that Mars had water once on the planet. And even like 3 years ago, when my colleagues were talking about this, there was a lot of debate about whether there was ever water, but I think that debate's really starting to come into a consensus that indeed there was. So I'm gonna just make you all a little smaller here. Okay, and just this is not a real image. Probably most of you recognize that, but it was created using this evidence that was collected from Mars and all these rovers. So biology and geology, that's not my thing. So that's why this talks about Mars atmosphere. If you want to learn more about those topics on Mars, then you'll have to wait for another speaker series person for that. But Perseverance does have some instruments on board that relate to the Mars air. For example, the microphones. And here are the locations of the 2 microphones on Perseverance. And if we go to this website, and I'm actually going to take us here because I'm going to play for you the sound, because I just think this is the coolest thing ever. Even though it's not my science, but who doesn't want to hear sounds from a rover on Mars? Well, maybe you don't, but I do. But I think actually when I shared my screen, I forgot to click share sound. So let me do that right now. Okay, so now let me try again. Okay, so this. Can you hear it? Very dim. So that's what sound is like on Mars. Was that successful? Can someone say yes or no?
Yes, that was successful.
Okay, thank you. That's hard in this virtual world to always know. Okay, so I'm going to go back to my...
We're all muted, by the way, so...
Yes, I appreciate the muting. Okay, hey, look at that. That worked well. Okay, so sound waves and air. So this is a little physics interlude. I'm a physicist by training, so you're going to have to just wait through it if you don't like physics, or enjoy it if you do. So on Mars, sound, if you didn't already know, are basically, it's a type of wave through our air. So when there is no air, there is no sound. So all those movies that have sound out in space, that's all just to make your experience of that movie enjoyable, because if it were actually real, it would not be as fun to watch those movies. So if you were out there in space, you would hear nothing because there's no air to make sound. So what's happening, like this little speaker right here, a little picture of a speaker, and then these particles represent the wave that is being made of air molecules, so the speaker moves back and forth, and what it does is it bunches up the air into a lot of particles in an area and little particles in an area. And as it moves back and forth, and then that wave propagates through to your ear, and then it interacts with your eardrum. So what I'd like you to do is in the chat, let me see if I can get my chat up here. In the chat, can you, I know Stephanie's like, okay. So in the chat, can you please put what you think might happen to the sound if you're in thin air? So if you climb up to Mount Everest or you jumped out of an airplane, how does the sound change when the density of air or the air is thinner, as we say? Okay, quieter, that makes sense. Higher pitch, could be. Lessons. These are all great guesses. So yes, the sound would definitely be lower, would be softer. And if you can imagine all these dots getting super, super diffuse, so a higher pitch means that this speaker would move back and forth faster. A lower pitch would be the speaker moving more slowly. So if you had fewer particles in here and you move it really fast, then you might be able to imagine that the particles are kind of going to dissipate before they really go very far. So high pitches essentially disappear. So that's one thing that happens. But yes, the propagation is faster as well, yes. Okay, so let's compare some other things about air on Mars compared with Earth. And here's another website that, you know, now that I have, sorry. Here's another website that you can go to, mars.nasa.gov/all-about-mars/facts. And I'm going to take us there for a minute because I just think this is another really cool NASA Mars page. So first of all, they've got this great interactive. Look at that. You can look all over Mars. Okay, that's cool, but that's not all. If you go down, then they have all these beautiful graphics. They have a little fact thing that you can save. It's the fourth planet from the sun. There are moons. Mars has some moons. The size of Mars compared to Earth and our moon. You can see it's kind of right in between there. The weight, if you were to go on Mars and you weighed 100 pounds, you would only weigh 38 pounds on Mars. And it shows kind of how far away Mars is from the sun and how many days it is, the volumes, the temperature, the structure. Okay, so that's enough of that. But you can keep playing there if you love that site. But we're going to go to the next slide, so I took this picture from that, that site. And what you see here is that the Mars's atmosphere, or Earth's atmosphere, is primarily nitrogen. And then we have 21% oxygen and 1% other. So clearly the oxygen is very important, and that's what we breathe. Now, if you went to Mars, Mars is 96% carbon dioxide. So for us, that is toxic. I asked my son, what do you want to know about Mars's atmosphere? And he said, is it toxic? So the answer is yes. Mars's atmosphere is toxic. And then there's argon, nitrogen, and other. Now, as most of you probably know, carbon dioxide is not toxic to everything, not all life. In fact, trees love carbon dioxide. They breathe it in, breathe out oxygen. So some people, of course, when they talk about terraforming Mars, they talk about adding trees and such things from Earth. And we already talked a little bit about this gravity, or just how much you would weigh. And so there's a nice little graphic of a person there moving from Earth to Mars. That's what that's supposed to represent. So walking would be pretty fun. So if we went to Mars, let's pretend we went to Mars like the rovers did. This is a picture from one of the rovers. And you might be able to see, if you clean off your screen, there's a little dot where that arrow is pointing. And that is what Earth would look like. It essentially looks like a star. So it's even less impressive than Mars is in our sky because it's white. Well, maybe a little blue, but so I thought that was cool. And you can see the air. You can't really see much air in this picture. There's maybe a little bit of evidence of air just from the glow here. But here you can see a lot of particles in the air. This is a sunset taken by another rover. And that's the sun, which of course looks smaller in the sky because Mars is farther away. And what do you think is making, go ahead and put in the chat, what do you think is making the sky look like that? Yes, exactly. Okay, so you all know about that. Yes, dust, exactly. All right, so the other thing that relates to air on Mars that is cool about Perseverance is this really cool helicopter called Ingenuity. And you can see Ingenuity sitting right over there. And this was this picture that NASA released called Perseverance Takes a Selfie with Ingenuity, which I thought was a clever social media tagline. And so I wanted to share that with you. Here are two closer pictures. So Perseverance is taking these pictures of its fellow sojourner here. So this is just from two different angles. And you can see there's some dust on the solar panels on this picture. These are the blades. There's some really cool interviews with the engineers who worked on Ingenuity, talking about what's so complex about creating a helicopter to fly on Mars. And on April 8th, that's yesterday, they did a demo of the blades turning. And I was trying to figure out when, because they had said they were going to fly on April 8th. So I thought I would show you all some cool flight from the helicopter. But alas, no. And now they say it won't happen earlier than April 11th. And this helicopter is simply there to prove that we can fly helicopters on Mars. Perhaps drones then could be another robotic way to explore Mars. And so again, here's our little physics interlude. So I just took this text from Wikipedia because I thought it was so well written. And I'm not expecting you all to just think this is fantastic, but I do. So thought I would share it. A fluid flowing around the surface of an object applies a force against it. It makes no difference whether the fluid is flowing past a stationary body or the body is moving through a stationary volume of fluid. Lift is the component of this force that is perpendicular to the oncoming flow direction. Lift is always accompanied by a drag force, which is the component of the surface force parallel to the flow direction. So while the flow of air, say in Ingenuity's blades, as the blades move along around the air, and then there are two forces happening. One is up, one's to push up on the blades, and the other is to drag it parallel to the blades. And here's a nice, you can't have a science talk without an equation. And just to prove that that flying a helicopter on Mars is going to be different than a helicopter on Earth, the way that you get a lift depends on the density of the air. So this is why we can't take helicopters past a certain altitude on our planet, because the air just gets too thin. So the air in the air on Mars is super thin for two reasons. What are those two reasons? Anyone know? Anyone take a guess? Put it in the chat why you think the air on Mars is thin compared to Earth. Low gravity keeps fewer molecules at the surface. Little or no oxygen. Low gravity. Okay, so low gravity is absolutely one of them. Because if Mars had higher gravity, was bigger and massive, then there would be more molecules at the surface. And so the other reason is because we've lost some of the atmosphere over time. All right, so there's evidence, as we mentioned, that there was once water on Mars. So this is kind of this graphic is supposed to represent Mars in the past and Mars today. So Mars in the past would be, of course, the right part of this globe of Mars, and the left part is today, and had a thick atmosphere, thicker. Of course, the gravity didn't change, but other things changed. So where did the water and air go? Hold on one sec. Okay. Where did the water go? So if we look at this picture here, where do you think the water and the air, where do you think it went over time? What happened to it? Why don't you put in the chat what you think happened to it? People are like, well, I don't know. The Martians ate it. No, I'm just kidding. That's right. The Martians drank it all. Dave's on my global warming. I love it. Escaped into space, blown away by solar radiation. Okay, cool. So there are two places it went. One is it went down. So soil can store water and gas, or the air. And it went up, as many of you said. It can escape to space. So good job, you all. You're on it. So some of the questions that we might have about this are, does the atmosphere just extend out into space? Does something block the atmosphere? Is space itself empty? Okay, so these are some of the questions you might have, or one might have, as they're thinking about this. So I'm going to let you just think about that for a little bit, and I'm going to tell you a little story about my life that's relevant to all of this. So I went to the University of Oregon. That's the math and science building where I had a lot of my classes. And I did, when I was there, I wanted to do research as an undergrad, and I went to Utah State and did a research experience and studied the Earth's ionosphere. And it was the first time in my life that I ever had heard the word ionosphere. So I would like to know in the chat again, have any of you heard of the word ionosphere before? I know many of you have. Ham radio guy, exactly. Woohoo, look at all our ham radio people. I love it. I just got my license recently. I'm gonna have to find you all. Okay, good. So this was, I don't know, how old was I? Probably 21. So I hadn't heard of the ionosphere. So you all have, so that's fantastic. You'll know then, it's up here. Some of you have not, I'm sure. Dad as a ham, yeah, I know. I got to teach my sons. Anyways, we'll get there. So this is kind of Earth. There's some glowing atmosphere and different altitudes. You have the ionosphere. It's called the thermosphere on Earth because it gets really hot in that area. The same sunlight that gets absorbed to strip electrons off of atoms to make what's called the ionosphere is also heating up the atmosphere. So that energy gets deposited in this area above 100 kilometers. Okay. And then I also learned about Earth's magnetic influence. So maybe some of you, I think our audience is old enough to know to know this critter and his wily ways. And if we take a compass and map out the force that a magnet has, then we can make these lines. We call them magnetic lines of force. And we can learn about how that magnetism is influencing its surrounding areas for the things that actually get influenced by magnetism. So what are some of the things? Oh, really? Oh, thank you, Dave. Okay. Is that better? Yes, thank you. Okay. Forget the chat. Someone's going to have to just tell me if people did it. Okay. So here is our magnetic field lines and a little compass needle. And the compass needle moves away from the north it points to a south magnetic pole and away from a north magnetic pole. So as a matter of fact, the south magnetic pole is in our northern hemisphere. That may or may not be a new thing to learn. And all sorts of things on our planet are influenced by magnetism. Cows, I read a Nature paper that showed that cows actually, when they're sleeping, they line north to south along the north-south magnetic field on Earth. Sharks are thought to use a magnetic sensor in their brain to navigate, as are turtles. So there's all sorts of cool, but like I said, I'm not a biologist, so I'm going to stop speaking about these critters before I get something wrong. We have magnetic fields as radiation shields. One way to protect ourselves from radiation getting to us is putting up a magnetic field around us. It will deflect radiation that has a charge. So electrons or ions or protons. And then I wanted to show this video here of again. So this is for those of you who do education and outreach. These are really nice three-dimensional compasses, or we call them magnetometers, things that measure magnetic fields. And so I thought I would just show. Whoops, what happened? I'm going to show you this video by going here. I think it's right here, actually. Yep.
Until we reach the North Pole.
Okay, we're going to start here.
What's the largest magnet in the world? The Earth, of course. Here's an activity that will link Earth science and physics concepts. It's also a great activity for elementary and middle school students. This small globe model has a bar magnet inside and is a great way to illustrate the Earth's magnetic properties. Now, I'm going to use a magneprobe to complete this demonstration. The magneprobe is essentially a three-dimensional compass that will show the direction of the magnetic field at any point. First, let's look at the equator. As we might expect, the compass points north and south. Moving farther north, the compass continues to point north until we reach the North Pole, where it points straight down to the Earth. Continue your journey around the Earth to the South Pole, where the magneprobe now points down. You can also use closed staples to illustrate the shape of the magnetic field around the Earth. Staples placed near the poles stand straight up and down. Staples placed near the equator lay flat on the globe. This interactive model is a fun way to experiment with the whole Earth.
Did you have fun? I had fun. Our scientific, I like them. Okay, but that was in no way, no. you could get it from anywhere. All right, so so I learned about magnetic fields and ionospheres and at Utah State, and I came back to University of Oregon, and I did a senior thesis comparing the ionospheres of Venus, Earth, and Mars. And so here's a picture of Earth's magnetic field. So if we took one of those magnet probes and then drew a line where that probe kind of moved out in space, this is exactly what happens on a satellite. So you can imagine a satellite orbiting our planet Earth, and it has a little compass on it, and that compass points in different directions with the magnetic field as it changes in space. It also changes in time. It's a very dynamic system. And so some of the folks down at UCLA, they made this lovely wire magnetic field. And so I was starting to read papers, this was in the 80s, about Mars. And I wanted to know, does Mars have a magnetic field? And this is just a representational graphic. It's back in the 80s, there had only been 2 satellites that had gone anywhere close to Mars. And one of the papers said, yes, there are magnetic fields on Mars. Mars has a magnetic field. It's not very strong, but it exists. And they wrote a whole paper about it. And then another group wrote a different paper saying from a different satellite and said, no, we disagree with the interpretation of the data on this other satellite because we see no magnetism and Earth does not have a magnetic field. And I remember wondering, it was like a mystery book to me, like, does Mars have magnetism or not? How can these 2 papers, and they were referring to one another, so clearly they had like met at conferences and argued about their data, and the papers were written very argumentatively. So I thought, what's going on here? Well, does Mars have magnetism or not? Well, I graduated and I took a ski break. I decided I wanted to ski, so I went to Colorado, and that was fantastic. Ski with my sister. And then I really missed physics and I wanted to do graduate school. So I went to Alaska where I could still be in snow, and I had a dog and she pulled me on my skis in Fairbanks, and that was super fun. And then this is my thesis advisor, Dr. Dirk Lumertsheim, who was just fantastic and a wonderful mentor to me. And this is just a physics formula shirt because of course we always had that out. And then this is the Geophysical Institute. My office was up at the top of there, right here. That was my window. And we would go up to this top of here and watch the Aurora Borealis. It was really great. And that's where I learned about the solar wind. This is a picture a picture from Earth of the moon blocking the bright sun. Excuse me. And when you're on Earth and you're in the shadow of the moon blocking the sun, you get this amazing total solar eclipse, which I think most of you know about. And you get these beautiful, you get to actually see this very dim corona and the chromosphere, this red part down here. And I just had to show another picture because I was at the 2017 eclipse, and this was a picture taken by my friend and colleague, Dr. Brian Mendez, and he gave it to me, and it just brings back such happy memories. This is the star Regulus there, and you can see these beautiful streamers, and this is kind of the beginning of the solar wind, this corona. This goes out into space, these particles, and they carry with them a magnetic field. And that magnetic field interacts with the Earth's magnetic field. So if you wondered kind of why is this all long on this side and short on this side? Why do you think that is? I mean, some of you know, and you can put the answer in, that's fine. The chat, let's put your answer in the chat. We can, now that I know it hides it, I can still look at it, but Zoom, come on. Okay, well, no, it's not letting me see the chat, so that's fine. Okay, so
said, pressure from solar winds, sun blows it out, solar winds blow it out, and then affected by solar winds from sun, question mark?
Yes, very, very good. Yes, affected by the sun, the solar winds, that's right. And in fact, you may have noticed up here on the top of my slides, all of my slides have these planets with a sun blowing towards them and blowing their magnetic fields out. So that is a good way to think about it, yes. So after I got my graduate degree, I went to the University of California, Berkeley, as Chris had mentioned, and there I studied the Aurora Borealis with a satellite called FAST, and learned about how the auroras how electrons come and make the aurora, which again is another talk. But what was really exciting related to this talk is that I met this woman named Dr. Janet Lumen, and she was one of the authors of one of the Mars papers. And she had written all these other papers about Venus, and I referenced her a lot in my, and I didn't know she was a woman because it was just Lumen et al. And then when I got there, I saw Janet Lumen, and so that was cool. I was like, oh my gosh, because she was famous in my head, and here she was. So it was great to meet her, and because I had read all her papers, and we talked a lot about Mars and the sun. And so one thing about the aurora that I also learned, kind of study a little more at UC Berkeley that relates to this talk, is that the aurora appears as ovals. If you look at Earth in ultraviolet light, that's what you're seeing here on this left side of this picture. So the UV that gives us suntans, it makes it all the way through the atmosphere, but a lot of it gets reflected back into space. And then the aurora ultraviolet light comes from electrons, kind of like a fluorescent light. And here's the same data, but just taking the auroral oval and adding it to a picture of Earth to give context. And just so you know, this aurora is occurring about 60 miles above sea level, 100 kilometers. And it is in Earth's upper atmosphere. So since we're talking about atmospheres, then in the upper atmosphere of planets, you can have auroras. And in fact, okay, so I just wanted to give you that context. The other thing that happened at UC Berkeley is that there was a group studying Mars Global Surveyor, and we've got someone picking up my kids, their dad. Hold on one second, I'm going to close my door. Oh, it's cool. Okay, good. So a little motion going on here. So this Mars Global Surveyor was it was basically the first orbiter to show back up at Mars since it was just like never before. It measured magnetic fields, it had an amazing camera on it, it orbited for a long time, it got just spectacular data. So I showed up as this data was coming in. And what I got to see at talks there was that Mars had what are called crustal magnetic fields. And so so what you're seeing here are the tracks of the satellites orbiting Mars, and it's looking down on Mars, but it's orbiting Mars at 400 kilometers, which is pretty close to the planet. And so each of these swaths is, as the satellite moves around Mars, it takes magnetic field data as one thing it does. And so here you're seeing that the red is magnetic fields of 1500 nanotesla, and the purple is the opposite polarity. So red is the north poles and blue are the south poles. And so you can see that there are these alternating north and south poles all over Mars, but they're mostly in the southern hemisphere. They're really predominantly in the southern hemisphere. And as a comparison, Earth's magnetic fields are about 50,000 nanotesla. So you can see these are very, very weak magnetic fields, but they are there, they exist, they're baked into the crust of the magnetic field. So there's not a global magnetic field like there is on Mars. And so this is so these two competing papers in the 80s, the reason is that they just measured different parts of the Mars system. So I love this parable. I don't know if you all know about this parable of the blind man and the elephant. And, you know, one man is saying, oh, elephants, they're long and they have, you know, they're snake-like, and they move, and they have this really strong, they've got this like hole, and another guy's arguing with him, no, that's not what an elephant is. An elephant's this big sturdy rock-like thing. And another one saying, no, that's not what it is. It is snake-like, but it's got this, it doesn't have a hole at the end. It's got this like tail thing. It's got these really you know, and so of course all of them are correct. They're just measuring or sensing different parts of the elephant. And so that's happens all the time in science, and is one of the challenges of studying large systems like we do. So after a lot of orbits of MGS magnetic field data, then one of my colleagues, Dr. David Brain, was able to make, along with a couple other folks, a plot of the magnetic field that looks like this. So you've got, this is Mars's magnetic field at 400 kilometers. And what you can see is down here, you have these kind of alternating magnetic fields. And if you were to make that into a 3D picture, then here on the right is what Dr. Brain calls his hairy ball model. Which I think is pretty hilarious. So this is kind of NASA's version of the crustal magnetic fields on Mars on the right, just as an animation. I mean, as just a graphic. It's not scientifically accurate. And here's kind of just a dipole field close up to Earth. And so we were wondering, Dave and I, would you find aurora on Mars? Because so auroras on Earth, they happen, remember I showed you that oval, and it's really in this area where the magnetic fields come down to the pole and make this oval around those. So we could see that there were kind of these regions between these crusts, these polarities here. And we wondered maybe aurora is made in these areas where there are these stronger magnetic fields. So we wrote a paper, we did some research and wrote a paper that you should see something like, you know, you might see some aurora in those areas. And then NASA MAVEN, a different satellite sent to Mars to study these things, measured aurora. And we were totally wrong. I mean, we were right, but they're so dim that you can't see them. And what dominates is this glow that comes. What do you think that's from? Any ideas? Maybe someone can read. Stephanie, can you read the chat? You can put it in the chat and read it to me.
I don't see anything in the chat yet.
Everyone's like, I don't know. Where does that ultraviolet come from on Mars? I'll give you a hint. It has something to do with winds. What kind of winds?
Sorry, the only one so far is a question mark. I think, oh, one said solar wind. Somebody said dust, static charge.
Okay, these are great.
I don't know why.
Yeah, these are great. Wonderful. Okay, great. I'm glad I asked. Good. So yes, so the answer is that the sun, that same sun that kind of blows off all this, these particles and magnetic fields and interacts with Earth's magnetic field, Mars doesn't have a giant magnetic field to protect its atmosphere from the solar wind. And so it actually hits the solar wind directly and excites those molecules, and then they glow. So here's a space, it's called a space weather event when you have a lot of solar wind, a lot of particles, high density, and a lot of magnetic fields. And so this just shows a bump compared to normal brightness. So this is the brightness, intensity is a brightness. So this is how bright the ultraviolet light was compared to what we normally see. And it was during a really big space weather event when we had a lot of really high density of particles from the sun coming by Mars. So knowing about that, I had asked, does the atmosphere just extend out into space? Does something block the atmosphere? Is space empty? And one of you, I think, had said that the solar wind might interact with with Mars's atmosphere, and it does. So the solar wind does, but also the light from from the sun, I'm sorry, the light from the sun can also interact with the upper atmosphere. It can break apart the carbon dioxide there and the nitrogen and creates carbon and oxygen and nitrogen atoms. And then just from the atmospheric circulation, meaning air moving around, then those, the carbon, oxygen, and nitrogen can be brought to the night where it's dark on Mars. And then then the air kind of gets pushed downward. And as they come down, then they recombine. And when they do recombine, they emit a photon of light. They emit a color, ultraviolet. So this is another way that ultraviolet is emitted from the atmosphere of Mars. So you have two ways. You've got the solar particles banging into the atmosphere of Mars and making it glow. And then you've got this complex chemistry that occurs in the upper atmosphere. Okay, so then I've got this movie that NASA put together that kind of shows the atmosphere changing with the solar wind conditions. So the arrows represent the wind coming off of the sun that is being carried by electrons and hydrogen hydrogen ions. And the colors are how much atmosphere in a given volume is in that area. So this is a very dense part of the atmosphere. And then this is a very diffuse, thin atmosphere. So what you can see is when the sun sends off a lot of particles, which we call a storm from the sun, that it can really strip off a lot of the atmosphere of Mars. So in the chat, I want you to write, why do you think that, or do you think this process happens on Earth? And if so, what atmosphere are we losing? And if not, why not?
And in the meantime, while we wait for responses from that, somebody had just a little earlier question a couple slides ago. What color does carbon dioxide glow at?
Ooh, that's a good question. Because it's a molecule with two oxygens and a carbon, it glows in a lot of different colors because there's vibrational bands as well as so there's just a lot of different colors you can make it glow.
And I'll read off some of the other answers to your other question. One person said yes. One said, I think our magnetic field protects us. One person said, we have the magnetic field that protects us from much of the solar wind, although we do lose some molecules. And then somebody else said, yes, but to a much lower degree due to protection of magnetic field here versus Mars.
Right. So, okay. So great. Those are great answers.
We asked if we can do multiple choice next time.
That's a good idea. I'll do a little that's hilarious. Okay, so I'm getting close to being done here. So I just want to read a couple sentences here, the kind of out of the Maven research that studied this idea of atmospheric loss. So Bruce Jakowski said that when protons and he learned that when protons and electrons from solar eruption slammed into the planet in March, they increased the rate at which Mars loses its atmosphere by roughly an order of magnitude, which means 10 times more than it was losing before that storm hit. So that's a lot of atmosphere loss. A second paper concludes only about 10% of the atmospheric particles that leave Mars are recaptured by its gravitational pull. The rest are lost to space permanently, because you can imagine some of that gets lost and then pulled back. But only 10% gets pulled back. And that new populations of charged and neutral particles, including oxygen, nitrogen, and carbon dioxide, are found at really low altitudes in the Martian atmosphere. So this is very surprising and relates to kind of the slide, the picture I showed of the oxygen, nitrogen, and carbon dioxide moving around the planet. So a lot of these questions, the last questions I asked you has not been answered. So we have, we being David Brain, who I was working with before, and several others, Yingxuan Ma from UCLA, and many others, one from University of New Hampshire, Kansas University. We currently have a phase 1 funding for a center called the Magnetic Fields, Atmospheres, and the Connection to Habitability Center. And what we're trying to study is whether a magnetic field is necessary to have life on a planet. Because the question is, does atmosphere get lost faster with a magnetic field or more slowly with a magnetic field? And there are some papers that have been published about loss of our atmosphere on Earth that show that it's really actually about the same rate as what's happening at Mars. But our atmosphere gets lost up at the poles, but also during solar storms. And so we're trying to understand what the role of this magnetic field is in losing atmospheres. And so we're also studying Venus and Mercury. And I think that's my last slide. Okay. That is all I have.
Thank you.
Thank you so much,
Thank you
Laura.
for coming. I know we're late, so, but I'm happy to stay a little later if anyone wants to stay and ask more questions.
Yeah, a couple people, I think around 7 had to pop off. One, Eric asked, does the atmosphere regenerate and how?
Oh, good question. The answer is yes. Basically, it comes out of the soil. Now, I don't know all the processes, but I do know, for example, Venus, it has a crust that reforms like every 100 years or something like that, like, or maybe it's 1,000, but it's like really recent. And in that process, it's churning up a lot of extra atmosphere. So Mars, I think Rachel said evaporation is one of the processes for losing air, or where could it go? And so we also have evaporation out of the ground.
So, Eric, so I would say that it doesn't, does that mean it doesn't actually regenerate? It just comes back out of the ground?
Well, it can also it can at the edge of space. Well, maybe I need to ask more about what you mean by regenerating. Tell me more about
is there a finite amount of oxygen on Mars? And when it goes away, aside from what is captured in the ground, which some of it comes back up again. So over time is sort of the total volume oxygen always going down, or does it actually come back up again?
I see what you're saying. Yes.
Stored or generated, it sounds like the question is.
No, it gets lost. That's correct. It gets lost over time. Yeah. You'd have to turn the carbon dioxide. You'd have to strip the oxygen off the carbon dioxide to increase, which does happen up high, at high altitudes. I mean, yeah, far from the planet. But then most of that gets stripped off. But some of it does come back down. It's complex.
And by the way, feel free to unmute yourselves. You don't have to write, I think at this point, write questions in the chat. But Tim asked, can you compare Venus' magnetic field versus Earth? If the field of Venus is weak, why isn't the atmosphere blown away?
Yes, this is the great question everyone asks. And we were discussing it actually a couple months ago at our team meeting. The primary reason is just Venus is bigger. And so it's able to hold on, the gravity's stronger, and it's just simply able to hold on to more atmosphere than Mars is. The other reason is because since Venus is closer to the sun creates, there's more ionosphere, more ionization that happens at the upper atmosphere, so that energy from the sun gets deposited up at the upper layers of the sun. You can think of the atmosphere as layers. So the sun's energy is deposited up there. And then what's super cool is that layer acts as protection for the sun to strip off any more particles. So it creates these ionospheric, these flux, what are called flux tubes, because the ionosphere gets so strong, and then the solar wind is kind of driving through that ionosphere, and it creates these complex magnetic fields that look like literally like rope. It looks like rope, and that protects the atmosphere of Venus.
And you talked about this in your team meeting. Boy, my team meetings are really boring compared to yours.
You should bring it up at your next team meeting.
I should.
As a non sequitur. Did you know? Either they'll love you or they'll hate you, but then you'll know who your friends will be.
Laura, I have a question. Are there any lessons we Earthbound folks can learn from what's happened to the Mars atmosphere? I mean, are there any general trends or?
Yeah, well, we're trying to figure that out. We were applying kind of what we knew about Earth to Mars, and then that didn't work out so well. And now we're realizing that we really need to kind of compare each planet a little more carefully. And the reason that David Brain got us all together is because typically scientists, we get so narrowly focused that we kind of, it's not necessarily that we couldn't know about Earth, like everything about Earth, but we might not ask the right question if we're not also looking at Mars. And vice versa. And so, like, I just saw this crazy talk at Sonoma State University where we had a guest speaker, and he studies black holes. And then their understanding of black holes fed back into an understanding of solid state physics. And he said, it's not that you had to learn this through black holes. It's just that when we saw it in black holes, we said, hey, that's kind of like solid state physics. And we just saw something that the people studying solid state physics hadn't noticed before. So I think that with this team, this interdisciplinary team looking at Mars and Venus and Earth, what we're hoping is that we kind of see things from each other's lenses that we hadn't noticed before.
Andy posted a question because his wife is listening to something else. So the carbon, oxygen, and nitrogen atoms were found lower than expected. How low did they go? And do we know?
No, that's a great question. So there's still a lot more to know about that. What's tricky about answering your question is data. So we have orbiters that orbit no lower than like 400 kilometers, because then they'll just enter into, they dip down to 100 kilometers. But if you go much lower than 100 kilometers, then the atmospheric drag becomes an issue. So then you can't stay in orbit for very long. And so typically missions aren't programmed to do that. Or you go right to Earth, right to the surface of Mars. And so if you go right to the surface of Mars, then you're too low. So there's this part of the atmosphere where we don't have the data. I think that they're seeing some of that as low as like 200 kilometers, but I haven't read a lot of those papers, so.
I have a question about Ingenuity and its aerodynamics. With the less dense atmosphere, is it compensated for by the less gravitational pull of Mars, or is there been a special adaptation to Ingenuity to make it fly? Or what would happen to Ingenuity in Earth's atmosphere?
Ooh, that's a great question. And I don't know the answer, actually. I would be guessing. I can guess, but I'll give you that caveat. But you all can guess with me. When I did watch the engineers talk about it before this talk, and they just said it was very tricky to fly on Mars, and that, yes, and I think that probably because, yes, you can, the trick is to get it up. So to get enough lift off of those helicopter blades that it even starts to go up. Probably once you get it up, then, it's going to take less time to go down because of the gravity. But you can also imagine the stability of such a system might be really difficult, because if you're trying to get the lift and your density is not high enough, then you might get it up, and then if it tilts just a little bit too much, then you could imagine that it's going to tip over completely. So I can imagine, and again, I'm just imagining from knowing how fluids go across things, but I think that that's the really tricky part, is to have enough stability so that it won't tip. And I would imagine, it should fly on Earth.
Well,
not knowing anything.
Lift equal drag for it to be stable, I would think, and less gravity and less air or whatever you call it, atmosphere, to provide the lift. So I just wondered how they adapted, bigger blades or whatever. Is it adapted to?
It probably takes another. Just guess. It probably takes more energy to spin the blades in Earth's denser atmosphere. So maybe the motors have to be beefed up. Andy asks if they're planning on getting a recording of what Ingenuity's rotor blades sound like on Mars.
That is a great question. I bet they will.
If I were the guy, I would I'd turn the mic on.
Me too.
I'm looking for the engineering discussion that I watched, because it sounds like some of you might like it. Okay, well, I'll if you, yeah, I think it was here.
And there's another question from Stephanie, although her thing says she's Zoom. So do weather balloons work on Mars?
That's a great question. Weather, well, they have weather stations on these rovers. Weather balloons, again, they're not going to go up very high because they can only, you have to fill them with something lighter than the atmosphere. Yeah, the density just has to be less than the atmospheric density. So that's going to be a little tricky on Mars, but possible. It just wouldn't go up very far. They have these. Yeah, go ahead, Rachel.
I was going to say, it's interesting to think about, since carbon dioxide is a fairly heavy molecule as far as gaseous molecules. So you could fill it with lots of different things that might be less dense.
That's true.
I don't know how it would work.
No, that's a really good point. And you would fill it on Mars. If you fill it on Mars, if you filled it on Earth and brought it, then you would have a problem. If you fill it on Mars, then the density is going to be low anyways because you're on Mars. Or maybe it doesn't matter, actually.
I don't know.
No, actually, I think it should go higher. I think you're right. I think Rachel's right, actually.
Throw in a little helium and it'll just go.
That's right, because carbon dioxide's way, yeah, that's right. It's way heavier than.
I have a question. It was really interesting watching, and thanks for the talk, Laura. It was interesting looking at those simulations with the solar wind coming in and how it really changes the thickness of Mars's atmosphere, right? It makes it really thin and dense when the solar storms are coming in. Did they talk about that in the engineering talk that you watched at all? Because I feel like there might be some, if there's a solar storm, that's a good time to try and fly the helicopter when the atmosphere is more dense. And I don't know.
Right. Well, I think that, so in that video, so let's look at that video again for a sec, because let me pull this up for a minute. I think we need to look at the scale to answer your question.
No.
I realized too, when I think I shared it again, my closed captions, well, I don't know. Okay, so let's look at this video again. Okay, so let me pause it. So this is probably 400 most of the atmosphere is in about 100 kilometers, just like Earth, actually. So this is probably 100 kilometers. That's my guess. So then, oh, look, I can loop it. There was a loop option. It went away. Okay, so then when it's really, really thin, it's probably still like 50 kilometers.
Yeah,
oh gosh.
Whoa, look at that. So I'm sure it might not be to scale, but it's just interesting to think about that as an additional challenge in engineering. If your atmosphere is changing even by 10%, as one of the numbers said, that can make a big difference on what your helicopter is going to do, I think.
Yeah.
How fun.
That is a really cool question. I'll be listening for an answer. I'll let you know if I hear anything. You let me know if you hear anything.
Okay.
All right. Wow. Well, you all have really persevered through this talk.
It's been great. Thank you for doing this.
Absolutely.
Very
Any
nice.
other questions?
Yeah, I have one. Do you know how windy it is? Is it, you were listening with the microphone there. You were listening to wind blow by, obviously. But how strong is that? That little helicopter going to go up and just get blown sideways?
Right. So the typical winds are about 10 to 20 miles per hour, but they can get up to 70 miles per hour during dust storms primarily. So now again, the atmosphere is a lot thinner, so that's going to feel a lot different than on Earth. But yeah,
so
they can.
The spoiler alert is that Mark Watney would have survived.
That's right. Yes, not that strong.
So when is the helicopter scheduled to fly?
After the, no sooner than April 11th. So what is that? That is Sunday.
Sunday is what I heard, yeah.
Yeah, so, but it keeps changing. Like every time I look, it changes. It was supposed to be the 8th. On the 7th, it was the 8th. And then they just did the rotation of the blades. And then there was no video of the rotation of the blades. I was going to put it in the slides. And then an hour ago, there was. So I stuck it in. So that I wanted to be current with you all in this talk. So keep your eyes out on the news.
Thank you so much, Laura. Thank you for being here and doing this. And it was fascinating as always.
Yes, thank you.
Well, thank you for coming, Laura.
So cool.
Good job.
Thank you. Nice to see you, Marilyn.
Thank you.
See you. Thank
so
you.
Many of you. Nice to see you, Andy, Rachel,
Dave,
and meet some of you.
When are you going to do this again?
I'll let you know. I'll Facebook it. not
Well,
the speaker series.
Plug for our June talk. Much of the equipment, these rovers and such, our June speaker is Dr. Bennell from the Space Sciences Lab, who's an engineer who designs, builds, and tests all manner of equipment that ends up in space. So,
do you have the date? At June what?
It's the second Friday in June, whatever that date is.
Okay.
It's and you can find it on our calendar, rfo.org.
And that too.
June 11th.
Or on rfo.simpletix.com is where you can sign up. I just put that in the chat. Or rfo.org. It's also on our calendar.
And you all have all your all of these recorded and put on your YouTube channel, is that right?
Yes.
Laura, I really enjoyed the one that you did for the docent